Hello and welcome to Late Physics. If you love exploring the universe in all its quiet, mind-bending glory, go ahead and hit that like button, and don't forget to subscribe so you never miss a journey into the cosmos. Now, before we dive in, where are you watching or listening from tonight? Whether it's from a cozy bedroom, a quiet study, or somewhere far from city lights, imagine that you're already halfway to the stars, because tonight we're venturing to some of the densest, most extreme objects in the universe. Neutron stars. These incredible remnants of once massive stars are more than just points of light in the sky. They're cosmic laboratories where gravity, quantum physics, and magnetic forces collide in ways we can barely recreate on Earth. In just a moment, we'll explore how matter is crushed to unimaginable densities, how these tiny spheres pack more mass than the sun into a space the size of a city, and how they spin, radiate, and bend the very fabric of space-time around them. So take a comfortable seat, let the world around you fade, and get ready to drift alongside the fascinating physics of neutron stars, a universe in miniature, hiding secrets that challenge the limits of what we think is possible. Hello, and welcome once more. Imagine a star, once blazing brightly in its prime, shrinking down over millions of years until it becomes something astonishingly small, yet unimaginably dense. These are neutron stars, cosmic laboratories where the rules of physics are pushed to their most extreme boundaries, far beyond what we can reproduce on Earth. A teaspoon of neutron star material, if you could somehow scoop it up, would weigh around 1 billion tons, as dense as the entire human population compressed into a sugar cube. It is in these tiny but massive spheres that the deepest questions of matter, energy, and gravity meet in a spectacularly intimate dance. Neutron stars allow physicists to explore quantum chromodynamics under conditions where neutrons are packed so closely that they touch, yet the star does not collapse. The strong nuclear force which binds protons and neutrons in atomic nuclei dominates here in ways that are impossible to replicate in a laboratory. This makes neutron stars natural particle accelerators, blasting electrons and protons into the surrounding space and emitting X-rays and gamma rays across the cosmos. Observatories like the Chandra X-ray Observatory and the European Space Agency's XMM Newton telescope have captured this high-energy radiation, revealing details about these compact titans that are as thrilling as they are complex. The history of understanding these stars is as fascinating as the stars themselves. Long before neutron stars were directly observed, scientists like Hermann Bonde explored the principles of relativistic astrophysics that underpin our modern models. Niels Bohr, while famous for his contributions to atomic structure, also speculated on neutron stability and the behavior of matter under extreme pressure, laying conceptual groundwork that would echo decades later in the study of these dense objects. Their work, combined with the calculations of Subrahmanyan Chandrasekhar on stellar collapse, provided the first glimpses into how massive stars end their lives and what is left behind after their explosive deaths. Consider for a moment the scale of a neutron star. The mass of our Sun, compressed into a sphere just about 20 kilometers across, means the gravitational field at the surface is roughly 200 billion times stronger than on Earth. Light itself struggles to escape, bending and twisting around the star in ways that test Einstein's general relativity to its limits. This extreme gravity also ensures that neutron stars rotate at dizzying speeds, sometimes spinning hundreds of times every second, a phenomenon first noticed in pulsars discovered by Jocelyn Bell Burnell in the 1960s. These rotating magnetic beacons emit pulses of radiation that sweep across space, like the lighthouse of a cosmic shore, and have become one of the most precise tools for testing fundamental physics. Neutron stars are not uniform. Their interiors reveal layers of increasing density and complexity. The crust, composed of neutron-rich nuclei and degenerate electrons, transitions to an outer core dominated by neutrons and a scattering of protons and electrons. Deeper still, in the inner core, matter may exist in forms that challenge our understanding entirely, potentially including hyperons, pion or kaon condensates, or even deconfined quark matter. Researchers like Danny Page and Sanjay Reddy have developed models of these interiors that combine nuclear physics with general relativity, using observations from X-ray timing and gravitational wave measurements to refine the theories. While neutron stars are extreme, they're also surprisingly diverse. Some rotate calmly and steadily, while others flare with bursts of X-rays and gamma rays as magnetars, magnetic monsters with fields 1,000 trillion times stronger than the Earth's. The European Space Agency and NASA have observed these outbursts, helping scientists like Yuri Lyuborsky and Andrei Beloborodov understand how magnetic reconnection and crustal stresses produce sudden energy releases. These phenomena remind us that even in the quiet emptiness of space, neutron stars are dynamic, alive with processes that push matter and energy to their limits. It is not only the physics of the stars themselves that fascinates, but also their role as engines of cosmic change. Neutron stars in binary systems can accrete matter from a companion, producing X-ray bursts and relativistic jets that shine across thousands of light years. These interactions, explored in detail by theorists like Johann Frank, reveal the interplay of gravity, magnetism, and angular momentum in ways that can be measured and studied. Observing these systems teaches us about the life cycle of stars, the creation of heavy elements, and the evolution of galaxies. Even on the level of thought experiments, neutron stars challenge our imagination. Their densities, magnetic fields, and rotation rates are unlike anything experienced on Earth. Yet, by observing them, calculating their equations of state, and modelling their interiors, we begin to glimpse how matter behaves under conditions that strain the very concepts of solid, liquid, and gas. They are, in every sense, natural laboratories, where each pulse, flare, and oscillation is a message from the universe about the nature of reality itself. As we embark on this exploration, picture yourself suspended above a neutron star, spinning silently, its surface gravity crushing everything toward its core, while beams of radiation sweep across the cosmos like invisible lighthouses. Think of the scientists, both famous and lesser known, who first glimpsed the possibilities of these objects and laid the foundations for our understanding. Imagine the interplay of nuclear forces, quantum principles, and relativistic gravity inside an object no larger than a city, but holding more mass than our Sun. In the coming moments, we will trace the life of massive stars, the violent supernovae that give birth to neutron stars, and the physical laws that govern their extreme interiors. We will observe the ways they spin, radiate, and bend space-time, and consider how their exotic matter and magnetic fields continue to puzzle and inspire physicists around the world. Neutron stars are both familiar and alien, tangible in the data we collect and yet fundamentally mysterious in their depths, inviting curiosity, wonder, and a quiet awe that lingers long after we turn our eyes away. By the end of this journey, you will have travelled from the heart of massive stars to the very edge of physics itself, understanding not only what neutron stars are, but why they matter as windows into the extreme universe, offering insights into the fundamental forces that shape everything around us. And even as you listen quietly from wherever you are, the story of these dense, spinning magnetic spheres will continue to unfold across the cosmos, one pulse, one flare, one whisper at a time. Stars are not eternal. They are born from vast clouds of gas and dust, slowly contracting under their own gravity until nuclear fusion ignites in their cores, releasing energy that balances the relentless inward pull. Massive stars, those with 8 times the mass of our Sun or more, live fast and spectacularly, burning through their fuel at rates that seem almost reckless in comparison to smaller, more measured stars like our Sun. Their cores fuse hydrogen into helium, helium into carbon, then carbon into neon, oxygen and silicon, and eventually, if the star is massive enough, the process culminates in the formation of an iron core. Iron, however, cannot release energy through fusion, so it marks the tipping point, the end of the star's ability to resist its own gravity. The internal life of a massive star is a delicate balance, orchestrated by the interplay between fusion pressure and gravitational collapse. Each stage of fusion proceeds faster than the last, with silicon burning lasting mere days, while hydrogen fusion can last millions of years. The rate of fusion depends not only on the star's mass, but also on its metallicity, the abundance of elements heavier than helium. Stars with higher metallicity radiate more efficiently, losing mass through stellar winds, which in turn affects the size of the core that will eventually collapse. Low metallicity stars, often found in early galaxies, retain more mass, producing more massive remnants, and sometimes leading to the formation of black holes rather than neutron stars. Among the more dramatic scenarios in massive stellar evolution are pair instability supernovae. In stars with extremely high mass, The intense temperatures in the core produce photons energetic enough to create electron-positron pairs, reducing the radiation pressure that holds the core up. This sudden loss of pressure causes partial collapse and explosive burning, leading to a supernova so powerful that it can completely disrupt the star, leaving no remnant behind. This process was first theorized in the 1960s and has been modeled with increasing precision by astrophysicists using complex simulations that capture the subtle interplay between relativistic effects, nuclear reactions, and core dynamics. Theoretical work by researchers like R.F. Sawyer has advanced our understanding of how these late-stage fusion processes interact with neutrino emission, convection, and rotational instabilities. Sawyer's models explore how angular momentum is distributed within the star, how rotation can support or delay collapse, and how magnetic fields, often twisted and amplified during stellar evolution, can influence the final collapse. Rapidly rotating cores can produce anisotropic supernova explosions, sending the resulting neutron star or black hole careening through space, with velocities of hundreds of kilometers per second. Magnetic fields also interact with charged particles in the core, subtly affecting the collapse dynamics and the structure of the resulting compact object. Rotation is not uniform throughout the star. The outer layers often rotate more slowly than the inner core, which retains the angular momentum of the original cloud from which the star formed. This differential rotation can generate turbulence and magnetic dynamos, creating fields millions of times stronger than those of the Sun. These magnetic fields can influence convection in the core, redistribute angular momentum, and even contribute to the launching of jets during the supernova. The combination of rotation and magnetic effects makes each massive star's death unique, shaping not only the explosion itself, but the properties of the neutron star or black hole that remains. As the star exhausts its nuclear fuel, the iron core grows until it exceeds the limit at which degeneracy pressure from electrons can support it, typically around 1.4 solar masses, known as the Chandrasekhar limit. At this moment, gravity wins decisively, and the core collapses in a fraction of a second. The implosion raises the density to nuclear levels, where neutrons are packed tightly together, creating the conditions for a neutron star. Neutrinos, produced in staggering numbers, escape and deposit energy in the surrounding layers, driving the supernova explosion that blasts the outer envelope into space. The shock wave can briefly outshine an entire galaxy, revealing the death of the massive star across millions of light years. The birth of a neutron star is not the end of the story. The rotation rate of the collapsing core determines how fast the newborn neutron star spins, sometimes hundreds of times per second. The magnetic field, amplified during collapse, shapes the emission of high-energy radiation and can power intense phenomena such as magnetar flares. Observatories, like the Chandra X-ray Observatory, the European Space Agency's XMM Newton telescope, and the Laser Interferometer Gravitational Wave Observatory, or LIGO, allow us to witness these cosmic events, from bursts of X-rays to ripples in space-time itself. Understanding massive star evolution requires a combination of nuclear physics, quantum mechanics, and general relativity. Each fusion stage alters the core composition, changing the balance of forces and influencing the path toward collapse. The interaction of rotation, metallicity, and magnetic fields means that no two massive stars die in exactly the same way. Some may form neutron stars spinning rapidly as pulsars, while others may collapse entirely into black holes. Even in death, these stars shape the universe, seeding interstellar space with heavy elements that will one day become planets, and perhaps life itself. Through it all, the work of both well-known and less heralded scientists continues to illuminate these processes. R.F. Sawyer's insights into neutrino transport, angular momentum, and core dynamics remind us that the details hidden deep inside the star have profound effects on the objects we eventually observe. By tracing the life and death of massive stars, we set the stage for understanding neutron stars not just as isolated curiosities, but as gateways to the most extreme and fascinating physics in the universe. And so, when we look up at the night sky, we are not merely seeing distant points of light. We are witnessing the ongoing story of stellar evolution, the fiery lives and explosive deaths of massive stars, and the birth of objects that compress the mass of our Sun into something smaller than a city. These are the crucibles in which the most extreme physics is forged, and by following their journeys we begin to understand the origins of neutron stars and the extraordinary conditions that define them. As a massive star reaches the end of its life, the balance between the outward pressure of nuclear fusion and the inward pull of gravity collapses. The iron core, having grown too heavy to be supported by electron degeneracy pressure, succumbs to gravity in a fraction of a second. This is the beginning of a core collapse supernova, one of the most dramatic events in the universe, where the very fabric of the star is thrown into violent motion, the core implodes, densities rise to nuclear scales, and temperatures soar to billions of degrees, creating conditions so extreme that even neutrinos, nearly massless particles, play a dominant role in transporting energy. The mechanics of core collapse are extraordinarily complex. Multidimensional simulations performed by research groups at the Max Planck Institute for Astrophysics and elsewhere reveal that the process is far from symmetric. Convection, turbulence, and standing accretion shock instabilities, or SASI, introduce variations in density and energy transport that shape the eventual explosion. These instabilities create pockets where matter accelerates differently, leading to asymmetrical ejection of the outer layers of the star. This is why supernova remnants are often irregular, and why neutron stars are sometimes found hurtling through space at hundreds of kilometers per second, a phenomenon known as pulsar kicks. The rotational state of the collapsing core adds another layer of complexity. Shinichiro Yoshida has investigated how differential rotation during collapse can create rotational instabilities, redistributing angular momentum and influencing the shape and dynamics of the forming neutron star. Rapid rotation can cause the core to flatten slightly at the poles, leading to uneven neutrino emission and contributing to the asymmetrical nature of the explosion. These rotational effects also determine how quickly the neutron star will spin after formation, sometimes resulting in pulsars with rotation periods of mere milliseconds. Magnetic fields, often amplified during the final stages of stellar evolution, interact with rotation and convective motion, creating magnetohydrodynamic instabilities. The interplay of rotation, magnetic fields, and turbulence can launch jets and outflows during the explosion, sculpting the supernova remnant and influencing the distribution of elements ejected into the interstellar medium. The energy deposited by neutrinos in the outer layers, combined with these mechanical instabilities, drives the shockwave outward, eventually tearing the star apart in a brilliant display that can outshine entire galaxies. Neutrinos themselves are a central part of the explosion mechanism. In the brief moments of core collapse, approximately 10 to the 57th neutrinos are emitted, carrying away most of the gravitational binding energy of the newly formed neutron star. Despite their weak interactions with matter, the sheer number of neutrinos ensures that a fraction interacts with the surrounding stellar material, depositing enough energy to revive the stalled shock front and power the supernova. Observatories such as the Super Kamiokande detector in Japan and the Ice Cube Neutrino Observatory in Antarctica aim to capture these fleeting particles, offering a direct glimpse into the heart of the explosion. The asymmetry of supernova explosions is critical to understanding the resulting properties of neutron stars. Variations in the collapse can lead to differences in mass, rotational speed, and magnetic field strength, imprinting unique characteristics on each newborn neutron star. Some may rotate slowly with modest magnetic fields, while others become magnetars, spinning rapidly and radiating enormous magnetic energy. These variations explain the diversity observed in neutron star populations and highlight the sensitivity of the final object to the chaotic dynamics of its parent star's death. Explosions also enrich the cosmos with heavy elements forged in the star's final fusion stages. Silicon, oxygen, and iron, along with elements heavier than iron produced in the shock and through rapid neutron capture, are dispersed into space, seeding future generations of stars and planets. The interplay between core physics and the ejection of material ensures that no two supernovae are exactly alike, with the details of rotation, magnetism, and neutrino-driven instabilities shaping both the compact remnant and the chemical fingerprint left behind. Simulations continue to refine our understanding, revealing phenomena that were once only theoretical. Rotational instabilities can lead to temporary bar-like deformations of the core. Gravitational waves ripple outward, and asymmetrical neutrino emission can subtly alter the momentum of the neutron star. These insights connect the chaotic, energetic processes of a dying star to the precise, observable properties of the neutron star it leaves behind. Each pulsar or magnetar we observe carries within it the story of its birth, encoded in spin, magnetic field, and motion through space. The formation of a neutron star is therefore a delicate balance between collapse and explosion, chaos and order. The imploding core, compressed to nuclear densities, becomes a sphere of neutrons held together by neutron degeneracy pressure, resisting further collapse into a black hole unless its mass exceeds the Tolman-Oppenheimer-Volkoff limit. Meanwhile, the outer layers are hurled outward in a supernova, their velocities, composition, and asymmetries dictated by the intricate interplay of rotation, magnetic fields, convection, and neutrino transport. Observationally, these events are breathtaking. Supernovae like SN 1972-5 or SN 2006 GI have been studied across the electromagnetic spectrum, from radio waves to gamma rays, revealing the signatures of these violent births. Meanwhile, gravitational waves and neutrino detections provide complementary data, confirming the complex dynamics predicted by multidimensional simulations. Each observation refines our models and deepens our understanding of how matter behaves under conditions that cannot be replicated on Earth. The birth of a neutron star is a story of transformation. A massive star sheds its outer layers, light and heavy elements are scattered into the galaxy, and at the core, matter is compressed to a density unmatched anywhere else in the observable universe. These newborn neutron stars, born spinning, magnetized, and unique, are the living remnants of a star that once shone brightly, now continuing to influence their surroundings in subtle but profound ways. By studying their formation, we uncover not just the mechanisms of stellar death, but the foundations of when the iron core of a massive star collapses under its own gravity, it reaches densities so extreme that ordinary matter as we know it cannot persist. At this point, neutrons are squeezed so tightly together that the very rules of quantum mechanics come into play, creating a pressure that resists further collapse. This is known as neutron degeneracy pressure, a concept first explored in detail by Lev Landau in the 1930s, who understood that the Pauli exclusion principle prevents identical fermions, such as neutrons, from occupying the same quantum state. It is this principle that provides the essential support holding a neutron star up against the immense pull of gravity. Unlike the pressure generated by heat or fusion in ordinary stars, neutron degeneracy pressure is purely quantum mechanical. It does not depend on temperature, which is why even a cold, newly formed neutron star can maintain its structure. Every neutron is forced to occupy its own distinct energy level, and as the core compresses, the available states fill up, creating a repulsive effect that grows stronger with increasing density. The result is a delicate equilibrium, where the inward pull of gravity is exactly balanced by the outward quantum mechanical pressure of neutrons crowded together at nuclear densities. Modern models of neutron star matter expand upon these early ideas. Gordon Baim and Christopher Pethick, working in the 1970s and 80s, developed sophisticated equations of state that describe how neutrons interact at such extraordinary densities. Their models incorporate both the degeneracy pressure and the nuclear forces that act between neutrons, providing detailed predictions of the star's structure, including the density, pressure, and composition of both the crust and the core. These insights allow astrophysicists to estimate properties such as radius, mass, and the speed of sound inside the star, and they form the foundation for understanding phenomena like pulsar timing and rotational glitches. Superfluidity is one of the most intriguing aspects of neutron star interiors. At densities exceeding that of atomic nuclei, neutrons in the inner core are thought to form Cooper pairs, similar to the electron pairs in superconductors, allowing them to flow without viscosity. This superfluid behavior has profound effects on the star's rotation. As the neutron star gradually loses angular momentum through electromagnetic radiation, the superfluid core can decouple from the crust, storing angular momentum in quantized vortex lines. Occasionally, these vortices shift or unpin, transferring angular momentum back to the crust and producing sudden increases in the observed spin rate, known as glitches. These events offer a rare observational window into the otherwise inaccessible interiors of neutron stars, connecting quantum mechanical theory directly to the precise measurements of radio astronomers. The maximum mass a neutron star can support is another fundamental question. Known as the Tolman-Oppenheimer-Volkoff limit, or TOV limit, it represents the point at which neutron degeneracy pressure, even when combined with nuclear forces, can no longer resist gravity. Current estimates place this limit around 2 to 2.3 solar masses, although the exact value depends on the equation of state, which is constrained by observations of pulsars and binary neutron star mergers. Beyond this threshold, the star cannot remain a neutron star and collapses into a black hole, marking the ultimate triumph of gravity over matter. Understanding the TOV limit not only informs astrophysics, but also tests the principles of general relativity and nuclear physics in regimes far beyond terrestrial experience. The crust of a neutron star is composed of a lattice of neutron-rich nuclei, immersed in a sea of electrons, providing rigidity and contributing to the star's moment of inertia. Beneath the crust, the outer core is primarily neutrons, with a small fraction of protons and electrons, and it is here that nuclear interactions become significant. In the inner core, densities may rise to several times that of atomic nuclei, opening the possibility of exotic states of matter, including hyperons, meson condensates, or even deconfined quark matter. Researchers use observations of neutron star masses and radii, coupled with gravitational wave measurements from detectors like LIGO and Virgo, to constrain these models, gradually narrowing the range of plausible equations of state. The physics of degeneracy pressure also has a tangible effect on the star's behavior. For example, the pressure gradient inside the star supports not only the weight of the overlying layers, but also governs the oscillation modes that can produce gravitational waves. These subtle ripples in space-time, detectable with modern interferometers, carry information about the star's internal structure and composition. By comparing observed gravitational wave signatures with theoretical models, scientists can infer properties such as core superfluidity, stiffness of nuclear matter, and even the presence of exotic phases, bringing quantum mechanics, relativity, and astrophysics into a single coherent picture. Another fascinating consequence of neutron degeneracy pressure is how it influences thermal evolution. Because the core is supported independently of temperature, neutron stars can cool primarily through neutrino emission without collapsing, allowing them to maintain stability over millions of years. Neutrino cooling is extremely efficient during the first 100,000 years, with the star shedding thermal energy at rates billions of times greater than the Sun's current luminosity. Observations of surface temperatures using X-ray telescopes like NICER and Chandra provide crucial data for testing models of superfluidity, core composition, and the thermal conductivity of neutron star matter. Quantum mechanical principles combined with relativistic gravity produce additional surprises. The interaction between the crust and superfluid interior can lead to oscillations called quasi-periodic oscillations, which are sometimes observed in X-ray light curves of magnetars. These oscillations carry direct information about the crustal rigidity and the coupling between layers, demonstrating that even the smaller-scale quantum effects have macroscopic consequences, observable across thousands of light-years. Ultimately, neutron degeneracy pressure is what allows neutron stars to exist at all. Without it, the immense gravity of a dense stellar core would crush the star into a black hole immediately. The combined work of Lev Landau, Gordon Baim, Christopher Pethick, and many others has revealed the delicate quantum balancing act that permits matter to resist collapse under conditions that defy everyday intuition. From the structure of the crust to the possible exotic phases of the inner core, degeneracy pressure shapes the mass, radius, rotation, and even the magnetic behavior of the star. By studying these quantum effects in a cosmic setting, physicists gain insight into fundamental forces that are otherwise inaccessible. Neutron stars, in their quiet, extreme persistence, are not merely celestial objects, they are natural laboratories, demonstrating how the laws of physics operate under the most extreme pressures, densities, and energies imaginable. Their stability, or lack thereof, is the story of quantum mechanics, nuclear interactions, and relativity all working together in perfect, delicate harmony, producing some of the most fascinating and extreme objects in the universe. The interior of a neutron star is a realm of extreme physics, layered in complexity and density in ways that challenge the imagination. At the surface, a thin atmosphere of hydrogen, helium, or heavier elements forms a delicate boundary, only a few centimeters thick, separating the star from the vastness of space. Beneath this lies the crust, extending roughly 1 kilometer inward, composed of neutron-rich nuclei arranged in a crystalline lattice and immersed in a sea of degenerate electrons. The crust provides rigidity, contributing to the star's moment of inertia and influencing phenomena such as starquakes and rotational glitches. It is here that the familiar principles of solid-state physics meet the extraordinary pressures of a neutron star, allowing scientists to draw analogies while appreciating the extreme scale of forces at play. Below the crust lies the outer core, extending to depths of around 10 kilometers, where the density rises to 2 to 3 times that of atomic nuclei. Here, neutrons dominate, but a small fraction of protons, electrons, and possibly muons are present. The strong nuclear force governs the interactions, creating a balance that maintains stability against further collapse. Theoretical models developed by researchers such as Danny Page, Sanjay Reddy, and Fridolin Weber provide insight into the equation of state in this region, predicting how pressure, density, and composition vary and influence observable properties like radius, mass, and cooling behavior. The outer core is also the site of superfluidity among neutrons and superconductivity among protons, which allows for nearly frictionless flow and has direct consequences for the rotational behavior of the star. Delving deeper, the inner core of a neutron star remains a subject of intense research and speculation. Densities may reach up to 10 times that of an atomic nucleus, producing conditions under which conventional nuclear matter may transition into exotic phases. Hyperons, particles containing strange quarks, may appear, altering the equation of state and influencing the maximum mass the star can sustain. Even more speculative are the possibilities of deconfined quark matter, where neutrons dissolve into a soup of their constituent quarks, or colour superconductivity, a phase in which quarks pair up in a manner analogous to Cooper pairs in conventional superconductors. These exotic states are theorized to affect thermal conductivity, magnetic field evolution, and rotational dynamics, linking microscopic interactions to macroscopic observables. Among the more visually evocative phenomena in the inner crust and outer core are the so-called nuclear pasta phases. At densities approaching nuclear saturation, nuclei can deform into shapes reminiscent of spaghetti, lasagna, or gnocchi. These structures arise because of the competition between the strong nuclear force and Coulomb repulsion among protons, creating complex patterns that influence mechanical and thermal properties of the crust. Nuclear pasta may affect neutrino scattering, heat transport, and the star's response to magnetic stresses, providing a direct bridge between subatomic physics and observable astrophysical behavior. Observations of neutron star cooling provide crucial tests of interior models. Thermal radiation from the surface, measured by X-ray telescopes such as NICER, allows scientists to infer the efficiency of heat transport from the core to the surface. The presence of superfluid neutrons and superconducting protons modifies the rate of neutrino emission, affecting how quickly the star loses heat over millions of years. Comparing observed cooling curves to theoretical predictions enables constraints on the composition, density, and phase structure of the interior, helping to distinguish between models that include exotic matter and those that do not. Magnetic field evolution is another observable phenomenon intimately connected to the interior structure. Magnetic flux is thought to be frozen into the superconducting protons of the outer core, evolving over time through processes such as flux tube movement and coupling to the crust. This evolution shapes the star's emission behavior, including X-ray and gamma-ray bursts in magnetars, and influences the spin-down rates of pulsars. By observing changes in magnetic field strength and configuration over decades, astronomers can infer the dynamics of the core and the interactions between crustal and core matter. Mass and radius measurements provide further insight into the interior. Using timing data from pulsars in binary systems, gravitational wave observations from mergers, and X-ray spectral analysis, scientists can constrain the equation of state and test predictions from models that incorporate hyperons, quark matter, and nuclear pasta. These constraints allow us to understand how compressible nuclear matter is at extreme densities, how much mass can be supported before collapse, and how the star's rotation and magnetic field interact with its structure. The interplay between microscopic physics and macroscopic observables is a defining feature of neutron stars. A shift in the behavior of neutrons in the core, a rearrangement of nuclear pasta, or the onset of quark deconfinement can have detectable consequences for spin irregularities, magnetic field evolution, or thermal emission. This connection allows astrophysicists to probe conditions that are impossible to recreate on Earth, turning neutron stars into natural laboratories where the laws of physics are tested in their most extreme forms. Even within the outer core, the precise distribution of neutrons, protons, and electrons influences transport properties such as thermal and electrical conductivity, which in turn affect the magnetic evolution and long-term cooling of the star. Neutrino processes, including the direct and modified Urca reactions, are sensitive to composition and density, linking particle physics directly to the star's observable thermal history. By combining observations across the electromagnetic spectrum with theoretical modelling, researchers like Danny Page, Sanjay Reddy, and Fridolin Weber are able to refine our understanding of the intricate dance between microphysics and the star's macroscopic behaviour. In addition to cooling and magnetic field evolution, the interior structure influences rotational dynamics. The coupling between the crust and the superfluid core governs the occurrence of glitches, sudden spin-ups that provide a window into the internal mechanics. The arrangement of nuclear pasta, superfluid vortices, and magnetic flux tubes all contribute to the star's response to angular momentum changes, linking quantum-scale phenomena to rotational observables. Ultimately, the interior of a neutron star is a layered world of extremes, from a rigid neutron-rich crust to a dense superfluid outer core, and a speculative exotic inner core. Each layer plays a role in shaping the star's observable properties, including its radius, mass, cooling rate, magnetic field, and rotation. By combining the detailed theoretical work of researchers with multi-wavelength and gravitational observations, astrophysicists can connect the minute details of particle interactions to the grand astrophysical behavior of these extraordinary objects. In contemplating the interior structure of neutron stars, one realizes that every pulse, glitch, and flare is a manifestation of complex physics occurring over scales vastly smaller than the star itself, yet influencing its global properties. From nuclear pasta and superfluidity to quark matter and color superconductivity, the hidden interior shapes the visible star, making neutron stars not only marvels of extreme physics, but also laboratories that illuminate the deep connections between microphysics and the cosmos at large. Neutron stars are not only dense and compact, they are also gravitational powerhouses, curving space-time around them in ways that stretch our understanding of physics. According to Einstein's theory of general relativity, massive objects bend the fabric of space and time, and the more massive and compact the object, the more extreme the curvature. Neutron stars, packing 1 to 2 solar masses into a sphere roughly 20 kilometers across, create gravitational fields so strong that light itself is forced to follow curved paths, producing observable phenomena that can be studied from millions of light-years away. One particularly intriguing effect is frame dragging, predicted by general relativity and first calculated in detail for astrophysical objects by scientists such as Eric Poisson. In a rotating neutron star, the intense gravitational field drags space-time along with it, twisting the surrounding space in the direction of rotation. This means that objects and even light near the star do not follow simple straight paths, but are subtly shifted by the motion of space-time itself. Frame dragging has measurable consequences for orbiting material, timing of pulsars, and the propagation of radiation, offering an opportunity to test the predictions of general relativity under conditions far beyond what can be achieved on Earth. The gravitational field around a neutron star also creates the phenomenon known as gravitational lensing. Light emitted from the surface of the star or from nearby accreting material is bent around the star's compact body. This effect allows observers to see portions of the star that would otherwise be hidden behind the horizon of the stellar surface, effectively increasing the apparent size of the star. In binary systems, where a neutron star orbits a companion star, lensing can alter the timing and intensity of received signals, giving astrophysicists a tool to probe the mass and radius of the neutron star. Precise measurements of these lens signals help constrain theoretical models of neutron star interiors and test strong field general relativity. Binary systems also provide natural laboratories for testing gravitational theories beyond Newtonian approximations. The timing of pulsars, which emit highly regular pulses of radiation, can reveal minute changes in orbital parameters caused by the curvature of spacetime, gravitational wave emission, and relativistic precession. Observations of pulsar binaries by research teams around the world, including those using the Parkes Observatory in Australia and the Arecibo Observatory in Puerto Rico, have confirmed Einstein's predictions with remarkable precision. These measurements also offer insight into how deviations from general relativity might appear, providing constraints on modified gravity theories such as scalar tensor models or Fauve-R gravity. Eric Poisson's work on relativistic stellar perturbations has been particularly influential in understanding how small deviations in a neutron star's structure, rotation, or magnetic field can influence the surrounding spacetime. By modeling perturbations in the star's gravitational field, researchers can predict phenomena such as quasi-normal modes, which may generate gravitational waves detectable by instruments like LIGO and Virgo. These waves carry information about the mass, radius, and internal structure of the star, linking gravitational theory directly to observable astrophysical signals. Rotation amplifies the effects of gravity in subtle ways. A rapidly spinning neutron star not only drags spacetime around it, but also exhibits centrifugal flattening at the equator, altering the local gravitational potential. This flattening affects the orbits of nearby particles, the shape of the magnetosphere, and the distribution of emitted radiation. High-precision X-ray timing measurements, such as those from NASA's NISA instrument on the International Space Station, can detect these distortions, providing further evidence for relativistic effects in strong gravitational fields. Magnetic fields interact with gravity as well, particularly in magnetars, which combine extreme magnetic intensity with the curvature of spacetime. The interaction of the magnetic field with the stellar crust and the superfluid core is influenced by frame dragging, affecting the stability and evolution of the magnetic configuration. Magnetic stress can also induce starquakes, sudden rearrangements of the crust that produce bursts of X-rays and gamma rays, observable across the galaxy. These events allow astronomers to infer both the strength of the magnetic field and the influence of relativistic gravity on the star's surface layers. Gravitational time dilation, another prediction of general relativity, plays a crucial role in neutron star observations. Clocks near the surface of a neutron star tick more slowly relative to distant observers, meaning that radiation emitted from the surface is redshifted. This effect is measurable in X-ray spectra, allowing scientists to calculate the star's compactness, defined as the ratio of mass to radius. The greater the compactness, the stronger the relativistic effects, and careful measurements of these shifts have provided some of the most stringent tests of strong field general relativity outside of black holes. In addition to general relativity, theorists have considered alternative models of gravity to explain extreme astrophysical phenomena. Scalar tensor theories, for example, predict subtle differences in the behavior of neutron stars under strong gravitational fields, including variations in spin evolution and orbital decay in binary systems. Observational data from pulsar timing and gravitational wave detections continue to place tight constraints on these models, demonstrating the utility of neutron stars as natural laboratories for testing the fundamental laws of physics. The gravitational field also shapes the behavior of accreted matter and surrounding plasma. Particles in the magnetosphere follow curved paths dictated by both gravity and magnetic forces, producing emission patterns that are highly sensitive to the star's mass, radius, and spin. By comparing observed pulse profiles to theoretical models, astronomers can infer details of the star's structure and the effects of general relativity, connecting the extreme curvature of spacetime to the patterns of light that eventually reach telescopes on Earth. In this way, gravity and spacetime effects are not merely abstract concepts, but central to the observable behavior of neutron stars. From frame dragging and gravitational lensing to time dilation and orbital dynamics, these stars provide a natural stage for exploring relativistic physics at its most extreme. Every pulse, every burst of radiation, and every gravitational ripple carries information about how matter and energy interact under conditions far beyond human experience, making neutron stars indispensable tools for testing our understanding of the universe. By studying these effects in detail, astrophysicists can link the theoretical principles of general relativity, relativistic perturbation theory, and even modified gravity to the observable properties of neutron stars. Rotation, magnetic fields, and binary interactions are all filtered through the lens of spacetime curvature, producing a rich tapestry of phenomena that continues to challenge and inspire scientists worldwide. In the compact, spinning, and intensely gravitating interiors of neutron stars, the interplay of gravity and matter reveals the profound elegance and complexity of the universe itself. Neutron stars are remarkable not only for their density and composition, but also for the astonishing speeds at which they can spin. As the core of a massive star collapses during a supernova, its radius shrinks from thousands of kilometers to mere tens of kilometers, conserving angular momentum in a process reminiscent of a figure skater pulling in their arms to spin faster. This conservation of angular momentum can transform a slowly rotating stellar core into a neutron star spinning hundreds of times per second, giving rise to one of the most precise natural clocks in the universe, the pulsar. Pulsars are neutron stars that emit beams of radiation along their magnetic axes, and as these beams sweep past Earth, they produce pulses of light that can be measured with astonishing regularity. Jocelyn Bell Burnell first discovered pulsars in 1967, revealing that these objects were not only compact and dense, but also capable of maintaining precise rotational periods over millions of years. The regularity of pulsar timing provides a unique window into their spin evolution, allowing astronomers to study angular momentum loss through electromagnetic radiation, particle winds, and interactions with their surroundings. The rotation of neutron stars is not always perfectly stable. R-mode instabilities, predicted in the 1970s and studied extensively by theorists such as Niels Anderson, arise from oscillatory modes in the fluid interior of a rapidly spinning star. These modes interact with the emission of gravitational waves, allowing the star to lose angular momentum and gradually spin down. The interplay between R-mode oscillations, viscous damping, and gravitational radiation provides a natural regulatory mechanism, ensuring that the fastest spinning neutron stars do not exceed critical rotational limits set by the balance of forces within their interiors. Some neutron stars experience a remarkable transformation through accretion in binary systems. In these systems, a neutron star draws material from a companion star, transferring not only mass but also angular momentum. This process, studied in detail by Victor Schwarzman and others, can spin the neutron star up to millisecond periods, creating what are known as recycled millisecond pulsars. These incredibly fast rotators often possess relatively low magnetic fields compared to younger pulsars, the result of accretion-induced field decay, and they demonstrate the dynamic interplay between mass transfer, rotation, and magnetic evolution. Observatories such as the Green Bank Telescope in the United States and the 500-meter Aperture Spherical Telescope in China have catalogued hundreds of these objects, revealing the diversity of spin behaviors across the neutron star population. The precise timing of pulsar rotation provides a direct probe into the star's interior. Sudden increases in rotation, called glitches, occur when superfluid vortices in the neutron star's interior unpin and transfer angular momentum to the crust. These events, first noticed in the Vela pulsar in the 1970s, offer a rare observational window into superfluid dynamics and the coupling between the crust and core. By analyzing the magnitude and frequency of glitches, scientists can infer the strength of the crust, the distribution of superfluid components, and the behavior of nuclear matter at extreme densities. Rotation also influences the neutron star's magnetic field. A rapidly spinning core can twist magnetic field lines, amplifying the dipole field and shaping the magnetosphere. The interaction between rotation and magnetism determines the structure of the pulsar wind, the acceleration of charged particles, and the emission of radiation across the electromagnetic spectrum. These processes are intimately connected to the equation of state, as the density, composition, and rigidity of the star influence how magnetic stresses are distributed and how rotational energy is dissipated over time. In addition to individual pulsars, the population statistics of spinning neutron stars provide insight into their evolution. Younger pulsars are often observed with longer rotation periods and stronger magnetic fields, while older, recycled pulsars exhibit shorter periods and weaker fields. This variation reflects both the loss of angular momentum through radiation and the spin-up effects of accretion, demonstrating the complex interplay between intrinsic stellar properties and external environmental influences. By studying large samples of pulsars in globular clusters, the Milky Way, and even nearby galaxies, astronomers can trace the life cycle of neutron stars from birth to their eventual spin-down over millions or billions of years. Gravitational wave astronomy adds a new dimension to our understanding of spin. Rapidly rotating neutron stars with slight asymmetries in their shape can emit continuous gravitational waves, carrying away angular momentum and subtly altering the rotation period. These effects, predicted by theorists and sought by observatories such as LIGO and Virgo, provide complementary information to electromagnetic observations, allowing researchers to constrain models of the star's internal structure and the rigidity of its crust. Rotation also affects the thermal evolution of the star. The distribution of centrifugal forces can modify the density profile, influencing heat transport from the core to the surface. Faster spinning stars may exhibit slightly different surface temperature patterns, observable through X-ray spectroscopy, while slower rotators show more isotropic thermal emission. Understanding these effects allows astrophysicists to link rotation with cooling, magnetic field evolution, and interior composition, building a holistic picture of how neutron stars evolve over time. Ultimately, the spin of a neutron star is both a legacy of its formation and a record of its ongoing interactions. From the conservation of angular momentum during collapse to the regulation by R-mode instabilities, from the dramatic spin-up in accreting binaries to the subtle glitches revealing superfluid dynamics, rotation connects the internal microphysics to the observable astrophysical phenomena. Each pulse that sweeps past our telescopes, each millisecond measured with precision, carries within it the story of the star's angular momentum history, its magnetic environment, and the extraordinary forces acting within its dense interior. By combining theoretical models, precise timing observations, and gravitational wave searches, scientists continue to uncover how rotation shapes the lives of neutron stars. The study of spin, rotation, and pulsars illustrates the intimate connection between fundamental physics and cosmic behavior, revealing how quantum mechanics, relativity, and magnetohydrodynamics all converge in these small spinning beacons of the universe. In the rhythm of their pulses, the extreme and intricate laws of nature are made observable, offering a mesmerizing glimpse into the dance of matter and energy under conditions far beyond anything on Earth. Neutron stars are not only dense and compact, but they also host magnetic fields of staggering intensity, far beyond anything experienced on Earth. These fields, often exceeding 1,000 trillion times stronger than the Earth's magnetic field, govern the behavior of charged particles, radiation, and even the structure of the star itself. Understanding these fields requires delving into the principles of magnetohydrodynamics, or MHD, which describes how electrically conducting fluids, such as the superfluid neutrons and superconducting protons in a neutron star's interior, interact with magnetic fields. The movement of these fluids and the evolution of the field are intimately coupled, creating complex dynamics that influence rotation, emission, and long-term stability. During the birth of a neutron star, the proto-neutron star phase is particularly important for magnetic field amplification. As the core collapses and the outer layers rebound in a supernova explosion, turbulent convection in the hot, rapidly rotating plasma acts as a natural dynamo, twisting and intensifying the magnetic field. This process can increase the field strength by several orders of magnitude in a matter of seconds. The resulting field configuration is often far from uniform, with regions of intense flux interwoven with weaker areas, creating a complex magnetic topology that shapes the star's subsequent evolution. Magnetas represent an extreme outcome of this process. These neutron stars possess magnetic fields so strong that they dominate the dynamics of the crust and magnetosphere, controlling particle motion and the emission of high-energy radiation. Theoretical models developed by scientists such as Yuri Lubarsky and Andrei Beloborodov explore how the magnetosphere of a magnetar behaves, showing that twisted field lines store enormous amounts of energy, which can be released suddenly in the form of flares. These flares, detected as bursts of X-rays and gamma rays, sometimes exceed the energy output of the Sun over hundreds of thousands of years, all released in a matter of seconds. Observatories like the Chandra X-ray Observatory, XMM Newton, and the Fermi Gamma Ray Space Telescope have captured these events, providing empirical data that refine and challenge theoretical models. The crust of a neutron star is not passive in this process. Magnetic stresses build over decades and centuries, gradually deforming the crust until sudden rearrangements occur, known as starquakes. These events release stored magnetic energy, producing observable bursts and sometimes altering the spin of the star. By studying the timing, intensity, and spectrum of these emissions, astrophysicists can infer the strength and configuration of the magnetic field, as well as the mechanical properties of the crust. The interaction between crustal rigidity and magnetic stresses is a delicate balance, and small variations can produce dramatically different outcomes, from gentle pulses to catastrophic flares. Magnetic fields also influence the rotational evolution of neutron stars. The torque exerted by the magnetic field on the surrounding plasma leads to gradual spin down, as rotational energy is carried away by electromagnetic radiation and particle winds. In rapidly rotating pulsars, this process occurs over millions to billions of years, slowing the star's spin and altering the alignment of the magnetic and rotational axes. The interplay between rotation and magnetic field structure affects the beam geometry, pulse profiles, and long-term detectability of pulsars, connecting interior physics to observable phenomena in a direct and measurable way. Observations of magnetars provide a window into extreme MHD phenomena. Giant flares, such as those recorded from SGR 1979-08 and SGR 2004-12, demonstrate that magnetic reconnection can release energies of the order of 10 to the 46 ergs, equivalent to the total energy the Sun radiates over 100,000 years. By analysing the light curves and spectra of these events, scientists can model the magnetic field geometry, estimate the energy stored in the magnetosphere, and investigate how internal dynamics propagate to the surface and beyond. These studies also help explain how less extreme neutron stars evolve over time, showing the continuum from ordinary pulsars to the most magnetic stars known. Magnetohydrodynamic instabilities play a central role in shaping the magnetic environment of neutron stars. The interaction of superfluid vortices, superconducting flux tubes, and differential rotation can induce small-scale turbulence, redistributing magnetic energy throughout the interior. This redistribution affects the large-scale magnetic geometry and can trigger observable phenomena such as quasi-periodic oscillations in magnetar bursts. Researchers have used numerical simulations to model these processes, revealing the feedback between magnetic stresses, fluid motion, and the star's rotation, creating a dynamic system that evolves over decades to millennia. The long-term evolution of a neutron star's magnetic field is also tied to the cooling of the interior. As the star radiates thermal energy and neutrinos escape, changes in temperature influence the conductivity of the crust and the mobility of superconducting flux tubes in the core. These effects alter the distribution of magnetic energy over time, potentially leading to shifts in pulse profiles, changes in spin-down rates, and even the reactivation of dormant magnetar-like activity in older neutron stars. Observational campaigns spanning decades provide the empirical data to test these theoretical predictions, highlighting the importance of persistent long-term study in astrophysics. Magnetic fields can also shape the radiation emitted from the neutron star. Charged particles trapped along magnetic field lines accelerate to near light speed, emitting synchrotron and curvature radiation across the electromagnetic spectrum. These emissions, detectable from radio waves to gamma rays, provide clues about the field strength, particle densities, and geometrical configuration. By combining multi-wavelength observations with magnetohydrodynamic models, scientists can reconstruct the internal and external magnetic structure, connecting microscopic plasma behavior to large-scale astrophysical phenomena. Even subtle asymmetries in the magnetic field can have profound consequences. A slight twist in the magnetosphere can focus energy in specific directions, creating hotspots on the star's surface and producing anisotropic emission patterns. These patterns, in turn, influence the star's rotational torque and the timing of pulses received on Earth. By studying these variations, researchers can infer details about the internal field configuration and the interaction between the core, crust, and magnetosphere, linking observations directly to theoretical models of MHD in extreme conditions. Ultimately, the magnetic fields of neutron stars and magnetars are central to understanding their behavior. From proto-neutron star dynamos and initial amplification to crustal rearrangements, flares, and long-term evolution, the fields govern rotation, emission, and internal dynamics. The work of theorists like Yuri Lubarsky and Andrei Beloborodov has shown that the magnetosphere is not a passive environment, but an active, dynamic system shaped by internal and external forces. Observations of X-ray and gamma-ray emissions combined with numerical modelling allow us to connect the exotic physics of the interior to phenomena visible across the galaxy, revealing the extraordinary interplay between matter, magnetism, and extreme gravity in these remarkable stars. In contemplating a magnetar, it becomes clear that we are witnessing the marriage of several extreme physical regimes: the crushing densities of the interior, the quantum behavior of superfluid and superconducting matter, and the staggering power of magnetic fields capable of reshaping the crust and energizing the surrounding space. Each flare, each subtle change in spin, and each pulse of radiation is a direct manifestation of these intertwined processes, allowing us to explore fundamental physics in a way that no terrestrial laboratory could ever achieve. The radiation emitted by neutron stars is as varied as it is extreme, spanning the entire electromagnetic spectrum from radio waves to gamma rays. Charged particles, accelerated to near light speed in the star's magnetic field, emit synchrotron radiation, spiraling along magnetic field lines and producing highly polarized light. In regions where the field lines curve sharply, these same particles produce curvature radiation, a mechanism that explains the narrow periodic pulses observed in radio pulsars. At even higher energies, inverse Compton scattering can occur, where low-energy photons gain tremendous energy by interacting with relativistic electrons in the magnetosphere. These processes, explored in detail by physicists such as W. Dietrich and H. Gies under the framework of quantum electrodynamics in strong fields, reveal the interplay of quantum mechanics and extreme magnetic environments in shaping observable emissions. Beyond the immediate magnetosphere, neutron stars influence their surroundings through pulsar wind nebulae. These are clouds of relativistic particles and magnetic fields ejected from the neutron star, forming intricate and often filamentary structures detectable in X-ray and radio wavelengths. In these nebulae, particle acceleration reaches extraordinary levels, with electrons and positrons gaining energies of up to 10 to the 15th electron volts. Observatories such as Chandra and the Very Large Array in New Mexico have captured detailed images of these nebulae, revealing dynamic structures that reflect the rotation, magnetic field, and energy output of the central neutron star. The patterns of radiation and motion in the nebula provide a direct link between the star's interior dynamics and the larger-scale astrophysical environment. Some neutron stars produce events of staggering intensity, gamma-ray bursts, among the most luminous explosions in the universe. Long-duration gamma-ray bursts are associated with the collapse of massive stars into neutron stars or black holes, while short-duration bursts can arise from the merger of neutron star binaries. These events release in seconds as much energy as the Sun emits over its entire 10 billion-year lifetime, illuminating distant galaxies and producing afterglows across X-ray, optical, and radio wavelengths. Multi-wavelength observations, coordinated across observatories like NASA's Swift satellite, the European Space Agency's Integral Observatory, and ground-based telescopes, allow scientists to study the temporal evolution of these bursts, revealing clues about the progenitor, the environment, and the extreme physics at play during the explosion. The emissions from neutron stars are not simply energetic displays. They provide critical insight into the star's interior and its equation of state. By analyzing the spectrum, polarization, and timing of radiation, astronomers can infer properties such as surface temperature, magnetic field strength, and the composition of the crust. For example, thermal X-rays emitted from the surface carry information about heat transport from the core, which is influenced by the presence of superfluid neutrons and superconducting protons. The interaction between the surface and magnetosphere, including hotspots and anisotropic emission patterns, allows constraints on the mass and radius of the neutron star, tying observational data directly to theoretical models of dense matter. Rotation plays a central role in shaping emission. Pulsars emit beams of radiation aligned with their magnetic axes, and as the star spins, these beams sweep across space, producing periodic signals detectable on Earth. The period, stability, and shape of these pulses provide high-precision measurements of the star's rotational dynamics, allowing detection of phenomena such as spin-down, precession, and glitches. Variations in pulse timing can reveal interactions between the crust and the superfluid core, or subtle shifts in the magnetic field configuration, offering a direct observational window into the star's interior physics. High-energy emissions are further influenced by the structure of the magnetosphere. Theoretical work by Yuri Lubarsky, Andrei Beloborodov, and others demonstrates how twisted magnetic fields and current sheets accelerate particles, creating localized hotspots and dynamic emission regions. These models show that the spatial distribution of radiation is highly sensitive to both the star's rotation and the underlying magnetic field geometry. Observations of sudden flares, quasi-periodic oscillations, and persistent high-energy emission allow scientists to test these models, providing constraints on the geometry, field strength, and particle populations within the magnetosphere. Inverse Compton and synchrotron processes are also important for understanding X-ray and gamma-ray emission from accreting neutron stars in binary systems. Material from a companion star forms an accretion disk, spiraling inward and interacting with the neutron star's magnetic field. Particles in the accretion column are accelerated, emitting high-energy radiation as they impact the magnetic poles, creating hotspots observable as pulsed X-ray emission. These observations allow measurement of the star's magnetic field strength, rotation period, and mass-to-radius ratio, linking surface phenomena to the dense interior. Multi-wavelength observation strategies are crucial for building a complete picture of neutron star emission. Radio observations provide precise pulse timing and information on rotation and magnetic alignment. X-ray and gamma-ray telescopes reveal surface temperature, magnetic activity, and high-energy particle populations. Optical and infrared measurements can detect accretion signatures or companion stars, while gravitational wave detectors such as LIGO and Virgo may capture oscillations or merger events that produce additional high-energy emission. By synthesizing data across these wavelengths, scientists can constrain theoretical models of the star's structure, composition, and magnetic field, connecting emissions to fundamental properties. The timing and spectrum of emitted radiation also inform models of neutron star cooling. Thermal photons carry information about heat flow from the core, influenced by superfluidity and the presence of exotic particles. Variations in surface temperature and emission anisotropy reflect both the magnetic field configuration and the distribution of crustal and core matter, allowing researchers to test predictions from models of dense nuclear matter. Observations over decades reveal trends in luminosity and spectral shifts, providing a long-term view of the star's evolution and interior physics. In extreme cases, gamma-ray bursts or magnetar flares provide natural laboratories for testing quantum electrodynamics in strong fields. Theoretical work by W., Dietrich, and H. Gies demonstrates how vacuum polarization and photon splitting can occur under the influence of magnetic fields exceeding 10 to the 15th Gauss. These effects subtly modify the emission spectra, providing a window into physics that cannot be replicated on Earth. By comparing observed spectra to theoretical predictions, scientists gain insight into the interactions between radiation, magnetic fields, and matter in ultra-strong environments. Ultimately, the radiation from neutron stars bridges the gap between the interior and the observable universe. Every pulse, flare, and burst is a message from the star's interior, encoding information about its density, composition, rotation, and magnetic field. Through careful observation across multiple wavelengths, and by connecting these observations to theoretical models of particle acceleration, magnetohydrodynamics, and quantum electrodynamics, astrophysicists can explore the extreme physics that governs these remarkable objects, revealing not only the behavior of neutron stars themselves, but also the fundamental laws that govern matter and energy at their limits. In many stellar neighborhoods, neutron stars are not isolated. They exist in binary systems, orbiting a companion star in a gravitational dance that can profoundly influence their evolution. When the companion expands during its stellar life, material may spill over the gravitational boundary known as the Roche lobe, flowing toward the neutron star and forming an accretion disk. This disk is a swirling, flattened structure of gas and plasma spiraling inward, heated to millions of degrees by viscous dissipation and gravitational potential energy. The physics of accretion disks involves complex interactions between gravity, rotation, and magnetic fields, and the study of these systems has been greatly advanced by theorists such as Johann Frank, who provided a framework for understanding how matter moves and transfers angular momentum in these extreme environments. As matter spirals inward, it encounters strong magnetic fields and differential rotation, conditions that can trigger magnetorotational instabilities. These instabilities amplify turbulence within the disk, enhancing angular momentum transport and enabling matter to accrete efficiently onto the neutron star. The result is a dynamic and sometimes chaotic environment where energy is dissipated across a range of wavelengths, producing X-ray emission that can be observed by space-based observatories. Instruments such as the Chandra X-ray Observatory, XMM Newton, and the Rossi X-ray Timing Explorer have captured these emissions, revealing detailed light curves, spectral lines, and bursts that provide insight into both the accretion process and the neutron star itself. X-ray bursts are among the most striking phenomena associated with accreting neutron stars. These bursts occur when the accumulated material on the neutron star's surface undergoes a runaway thermonuclear reaction, releasing energy equivalent to the sun's output over tens of thousands of years in a matter of seconds. The frequency, intensity, and spectrum of these bursts are influenced by the accretion rate, composition of the material, and the local gravitational acceleration at the neutron star's surface. Observing and modeling X-ray bursts allows astrophysicists to constrain surface gravity, mass, radius, and the equation of state of dense matter, connecting energetic surface phenomena to the deep interior. Accretion also has profound effects on the rotation and magnetic field of the neutron star. As material with angular momentum falls onto the star, it can spin the neutron star up, creating the so-called recycled millisecond pulsars. These rapidly spinning stars with rotation periods of just a few milliseconds often exhibit weaker magnetic fields than younger pulsars, a consequence of accretion-induced field decay. The interplay between accretion torque, magnetic stresses, and spin evolution demonstrates the delicate coupling between external material inflow and the star's internal dynamics. In some cases, accretion can also align the magnetic axis with the rotational axis, subtly modifying the geometry of emitted radiation and the structure of the magnetosphere. Relativistic jets are another remarkable product of accretion. When the inner regions of the disk interact with the neutron star's magnetic field, particles can be accelerated to velocities approaching the speed of light, forming narrow, collimated outflows. These jets are observed in both X-ray and radio wavelengths, and provide a window into the mechanisms of angular momentum extraction and energy release. The physics of jet formation depends critically on the magnetic field configuration, the spin of the neutron star, and the structure of the inner accretion disk, illustrating the intimate connection between rotation, magnetism, and mass transfer in binary systems. Tidal interactions between the neutron star and its companion also influence accretion dynamics. Gravitational forces can distort the companion star, creating periodic variations in mass transfer and shaping the structure of the accretion disk. These tidal effects can induce precession in the disk, modulate X-ray emission, and even affect the spin evolution of the neutron star itself. Observations of periodic changes in X-ray flux combined with theoretical modeling allow researchers to reconstruct the three-dimensional structure of the accretion environment and the orbital parameters of the binary system. The distribution of magnetic flux in the neutron star's magnetosphere plays a crucial role in guiding the accreting material. Magnetic field lines funnel gas toward the magnetic poles, creating hotspots wherein falling matter releases kinetic energy as X-rays. The location, temperature, and emission patterns of these hotspots provide information about the strength and geometry of the magnetic field, as well as the star's rotation rate. Multi-wavelength observations of these systems, including optical and infrared monitoring of the companion star, provide a comprehensive view of the binary interaction, linking external accretion dynamics to internal stellar properties. Accretion-induced spin-up and the resulting formation of millisecond pulsars also demonstrate the long-term consequences of binary evolution. These stars serve as precise cosmic clocks, with pulse periods stable enough to detect subtle effects such as gravitational waves from orbiting companions or variations in the moment of inertia caused by internal dynamics. By studying the timing of these pulses, scientists can infer the distribution of mass within the star, the state of the superfluid interior, and the interaction between magnetic fields and rotation. The complex interplay between accretion, rotation, and magnetism can also lead to episodic phenomena, such as type 1 X-ray bursts and magnetically powered flares. Each event provides a snapshot of the energy transfer processes at work, from the gravitational potential energy of infalling matter to the magnetic reconnection events that release energy from the star's field. Observations of these transients combined with theoretical simulations of accretion disks and magnetospheres allow astrophysicists to connect high-energy phenomena to the underlying microphysics, including superfluid vortices, crustal rigidity, and nuclear reactions at the surface. By integrating observations across the electromagnetic spectrum and comparing them to models of accretion and magnetic interaction, researchers can build a comprehensive picture of how matter, angular momentum, and energy flow through these binary systems. the behavior of the accretion disk, the formation of relativistic jets, the production of X-ray bursts, and the spin-up of recycled pulsars are all interconnected, revealing the profound influence of external material on the evolution of neutron stars. In essence, binary systems provide a natural laboratory for exploring the physics of accretion, angular momentum transfer, and magnetic field evolution under extreme conditions. From Roche-Lobe overflow and magnetorotational instabilities to X-ray emission and relativistic jets, these interactions illuminate both the behavior of the neutron star itself and the environment in which it resides. By studying these systems, astrophysicists gain insight into the dynamic processes that shape the lives of neutron stars, connecting observable phenomena to the underlying physics of some of the densest and most fascinating objects in the universe. The internal structure of a neutron star is governed by the equation of state, a relationship that links pressure, density, and temperature in the star's matter and determines how it responds to the immense forces at play. Unlike ordinary matter, the material inside a neutron star reaches densities several times that of atomic nuclei, producing conditions where quantum chromodynamics and nuclear interactions dominate. Understanding the equation of state, or EOS, is central to predicting the star's radius, mass, and response to rotation and magnetic fields, as well as interpreting observational data from pulsars, X-ray emissions, and gravitational waves. Several nuclear models have been developed to describe the behavior of dense matter. The APR model, developed by Akmal, Pantaripande, and Ravenhall, incorporates realistic 2- and 3-body nuclear interactions and has been widely used to predict neutron star structure. The SLY model, derived from SCIRM-type effective interactions, provides alternative predictions for pressure and density relationships, particularly in the crust and outer core. Chiral effective field theory, or chiral EFT, takes a different approach by systematically including the symmetries of quantum chromodynamics and providing a framework for extrapolating nuclear forces to the high densities found in neutron stars. Each of these models predicts slightly different relations between pressure and density, resulting in variations in predicted mass-radius relations and internal structure. In more massive neutron stars, additional degrees of freedom may appear in the interior. Hyperons, particles containing strange quarks, can form in the core when densities exceed a few times that of atomic nuclei, softening the EOS and influencing the maximum mass the star can sustain. At even higher densities, quark matter may deconfine, producing a core composed of up, down, and strange quarks, and possibly entering exotic phases such as color superconductivity. These possibilities, explored in part by researchers such as James Latimer, Madhapa Prakash, and Fridolin Weber, complicate predictions of the star's maximum mass, radius, and deformability, while offering a window into physics beyond the reach of terrestrial experiments. Observational data provide critical constraints on these theoretical models. Gravitational wave measurements from neutron star mergers, such as the landmark detection of GW17047 by the Laser Interferometer, Gravitational Wave Observatory and Virgo, give information about tidal deformability, a property that depends sensitively on the EOS. By analysing how two neutron stars distort each other's shape as they spiral inward, scientists can place limits on the stiffness of nuclear matter, which in turn constrains possible radii for stars of given masses. Similarly, X-ray observations from the NICER instrument on the International Space Station allow precise measurements of mass and radius, refining models of dense matter and testing predictions from APR, SLY, and chiral EFT. The EOS also influences the maximum mass a neutron star can support before collapsing into a black hole. Observations of massive pulsars such as PSRJ 0437-1218, with a mass of approximately 2 solar masses, set a lower bound for the TOV limit and eliminate softer equations of state that cannot support such masses. By combining mass and radius measurements, along with gravitational wave data, researchers can narrow the range of viable models, bridging the gap between nuclear theory and astrophysical observation. Deformation under rotation provides another window into the EOS. Rapidly spinning neutron stars are not perfectly spherical. Centrifugal forces cause flattening at the poles, and the degree of this ablateness depends on the stiffness of the matter. A stiffer EOS produces a larger radius for a given mass, leading to a greater equatorial bulge, while a softer EOS results in more compact, less deformed stars. Observations of rotationally induced gravitational wave emission, or limits on it, provide additional constraints, helping to determine how matter behaves under extreme compression and spin. Accretion from a companion star also interacts with the EOS. As material piles onto the neutron star's surface, the added mass increases central density and pressure, altering internal structure and potentially inducing phase transitions in the core. These changes can influence rotational dynamics, magnetic field evolution, and the onset of phenomena such as starquakes or glitches. By monitoring accreting pulsars in X-ray binaries, astrophysicists can probe how the equation of state governs the response of matter to gradual mass accumulation over millions of years. Temperature plays a subtler role in the equation of state. While the pressure from neutron degeneracy dominates, finite temperature effects influence the composition and phase of the outer layers, particularly during the proto-neutron star phase immediately after formation. Neutrino emission and thermal pressure can slightly modify the structure, but the bulk properties of the star are primarily determined by the zero-temperature EOS. By studying young neutron stars and comparing theoretical cooling curves to observed temperatures, researchers gain insight into the interplay between thermal effects and the dense matter equation of state. Exotic phases in the inner core, such as quark matter or hyperon-rich matter, also affect tidal deformability, moment of inertia, and spin evolution. The presence of softer components, for example, can make the star more compressible, influencing its radius for a given mass and modifying the response to rotational or tidal forces. Numerical simulations incorporating these possibilities show that small changes in the EOS can produce measurable differences in gravitational wave signals, providing a direct link between the star's microphysics and astrophysical observations. By combining nuclear theory, astrophysical modeling, and precise observational data, scientists can connect the behavior of individual particles within the dense core to macroscopic properties such as mass, radius, rotational stability, and magnetic evolution. The work of Latimer, Prakash, and Weber demonstrates how detailed equations of state, grounded in nuclear physics, can be tested and refined using real astronomical observations, creating a dialogue between theory and the cosmos. Ultimately, the equation of state serves as the blueprint for understanding neutron stars. It dictates how matter behaves at extreme densities, sets limits on mass and radius, influences rotational and magnetic dynamics, and governs the star's response to accretion and tidal forces. By studying EOS models alongside multi-wavelength observations, X-ray spectroscopy, pulsar timing, and gravitational wave data, astrophysicists are able to reconstruct the interior architecture of neutron stars, bridging the microscopic world of particles with the grand scale of astrophysical phenomena. In these dense, spinning magnetized spheres, the equation of state is the key to unlocking the deepest secrets of matter under the most extreme conditions imaginable. Binary neutron star mergers are among the most dramatic events in the cosmos, where two incredibly dense objects spiral toward each other under the inexorable pull of gravity. As the stars orbit closer, they emit gravitational waves, ripples in the fabric of space-time first predicted by Einstein over a century ago, carrying energy and angular momentum away from the system. This emission causes the orbit to shrink, accelerating the inspiral until the two neutron stars collide in an event of unimaginable energy. The dynamics of this inspiral and merger are complex, involving strong field gravity, tidal interactions, relativistic hydrodynamics, and magnetic effects, all occurring on timescales of seconds yet influencing phenomena that unfold over months and years. Simulations of these mergers have been essential for understanding the detailed physics involved. Researchers such as Masaru Shibata and Luciano Rezzolla have developed high-resolution numerical models that capture the relativistic dynamics of the stars, the formation of transient hypermassive remnants, and the ejection of material into space. These simulations show that the tidal forces deform the neutron stars significantly before collision, and the resulting merger produces shock waves, differential rotation, and turbulence that shape the immediate post-merger environment. The models allow scientists to predict gravitational waveforms, electromagnetic counterparts, and the distribution of matter that is expelled during the collision. One of the most remarkable outcomes of a binary neutron star merger is the generation of multi-messenger signals combining gravitational waves, electromagnetic radiation, and particle emission. The detection of GW 17047 by the Laser Interferometer, Gravitational Wave Observatory in Virgo in 2017 provided the first direct observation of a neutron star merger through gravitational waves. This event was accompanied by a kilonova, an optical and infrared transient powered by the radioactive decay of heavy elements synthesized in the ejected material. The kilonova confirmed that these mergers are primary sites for R-process nucleosynthesis, the rapid capture of neutrons that produces roughly half of the elements heavier than iron, including gold and platinum. The amount of mass ejected during a merger can range from a few hundredths to several tenths of a solar mass, depending on the mass ratio, spin, and equation of state of the neutron stars. This matter forms an expanding cloud of neutron-rich material that cools and undergoes nuclear synthesis, producing a rich array of heavy nuclei. Observations of kilonovae provide direct evidence of these processes, allowing astrophysicists to connect the dynamics of the merger to the chemical evolution of galaxies. The interplay between mass ejection, neutrino emission, and radioactive decay is a key aspect of multi-messenger astronomy, linking extreme physics to observable signals across the electromagnetic spectrum. The fate of the merged remnant depends on the total mass and internal physics of the colliding stars. If the combined mass is below a critical threshold, the remnant can remain temporarily as a hypermassive neutron star, supported by differential rotation and thermal pressure. These hypermassive stars can survive for tens of milliseconds to several seconds before collapsing into a black hole, or in some cases, they may shed sufficient angular momentum and mass to stabilize as a massive neutron star. The transient nature of the hypermassive state is crucial for understanding post-merger emission, as it drives the production of gravitational waves, electromagnetic radiation, and relativistic jets. Relativistic jets can form along the rotation axis of the merger remnant, powered by accretion onto the central object and the amplification of magnetic fields during the collision. These jets are thought to produce short gamma-ray bursts, brief but extraordinarily luminous events detectable across the universe. Observatories such as NASA's Fermi Gamma-Ray Space Telescope and the Neil Gehrels Swift Observatory have captured these bursts, providing timing and spectral information that complements gravitational wave data. The combination of gravitational and electromagnetic signals allows scientists to reconstruct the merger process in unprecedented detail, connecting observable phenomena to the underlying physics of ultra-dense matter. The gravitational waveforms from mergers carry signatures of the equation of state of neutron star matter. As the stars approach each other, tidal deformation depends on the stiffness of the material, affecting the phase and amplitude of the waves. Softer equations of state produce more compact stars that are less deformed, while stiffer matter results in larger tidal bulges. By analyzing the gravitational wave signal, scientists can infer the radii and internal structure of the stars, placing constraints on models of dense nuclear matter. This direct link between observation and theory allows for testing predictions from A, PR, SLY, chiral EFT, and other nuclear models under conditions far beyond those achievable in terrestrial laboratories. Post-merger dynamics are also influenced by magnetic fields, rotation, and differential motion within the remnant. Magnetic field amplification occurs through magneto-rotational instabilities, driving turbulence and redistributing angular momentum. These processes affect the lifetime of the hypermassive neutron star, the energy available to power relativistic outflows, and the characteristics of the emitted radiation. Detailed simulations by Shibata, Rizzola, and their collaborators demonstrate how the coupling between magnetic fields and fluid dynamics shapes both gravitational wave emission and electromagnetic observables. The observations of GW 17047 and its associated kilonova have provided a wealth of information about neutron star interiors, confirming that neutron-rich matter can survive extreme compression and that mergers are sites of rapid nucleosynthesis. By comparing these events to simulations, astrophysicists can refine the EOS, test models of hypermassive neutron star stability, and predict the outcomes of future mergers. Each merger acts as a natural experiment in strong field gravity, relativistic hydrodynamics, and nuclear physics, bridging the gap between theory and observation. Even the rotation of the remnant plays a critical role. Rapidly spinning post-merger objects emit gravitational waves at characteristic frequencies, which can be used to probe the distribution of mass and the internal composition of the merged star. Observing these frequencies, along with the associated electromagnetic signatures, provides constraints on superfluidity, hyperon content, and possible quark matter phases. The combination of spin, mass, and emitted radiation offers a comprehensive view of the extreme physics at work. Ultimately, binary neutron star mergers are windows into the most extreme environments in the universe. From in-spiral to collision, from gravitational waves to colonovae, these events connect fundamental physics, astrophysics, and cosmochemistry. By studying the detailed waveforms, emissions, and nucleosynthesis products, scientists can uncover the properties of dense matter, test the limits of general relativity, and understand the formation of heavy elements. In every gravitational ripple and burst of light, the story of matter under the most extreme conditions is written, offering a profound glimpse into the dynamic and interconnected universe. Beneath the crust and outer core of a neutron star lies a realm where matter reaches densities so extreme that the familiar rules of nuclear physics begin to give way to more exotic possibilities. At these densities, the distinction between individual neutrons and protons may dissolve, giving rise to deconfined quark matter, a state where quarks move freely rather than being bound within nucleons. One of the most compelling possibilities is the color-flavor-locked phase, in which up, down, and strange quarks pair in a highly symmetric superconducting state. This phase was extensively studied by theorists including Edward Witten and Mark Alford, whose work demonstrated that such arrangements could exist at the densities and pressures present in neutron star cores, profoundly influencing their macroscopic properties. Color-flavor-locked quark matter affects a neutron star in multiple ways. The pairing of quarks reduces the star's heat capacity and alters neutrino emission rates, influencing thermal evolution and cooling. Observationally, this can manifest as lower surface temperatures in young neutron stars than predicted by models based solely on conventional nuclear matter. Additionally, the presence of quark matter changes the stiffness of the equation of state, potentially reducing the radius of a neutron star for a given mass. By comparing radius measurements from instruments like NICER with theoretical predictions, astrophysicists can test for the presence of such exotic phases, using subtle differences in macroscopic properties to probe the microphysics deep within the core. Another fascinating consequence of extreme densities is the potential formation of strange quark stars, objects composed entirely of up, down, and strange quarks. These stars may be more compact than ordinary neutron stars and can exhibit unique rotational and thermal behavior. Hybrid stars, which contain both conventional nuclear matter and a central quark core, offer an intermediate possibility, with outer layers resembling typical neutron stars and cores, exhibiting the exotic properties of deconfined quarks. These theoretical constructs allow scientists to explore how matter behaves under conditions far beyond laboratory capabilities, linking microscopic quark interactions to observable astrophysical phenomena. Exotic matter also encompasses the possibility of Bose-Einstein condensates of kaons or pions in the inner core. Under extreme pressure, these mesons can condense into a single quantum state, forming a superfluid-like phase that alters the star's internal pressure profile. The presence of such condensates affects rotation, as the coupled superfluid dynamics can influence the timing and amplitude of pulsar glitches. Similarly, thermal evolution is modified, since condensates can change neutrino emission rates and heat transport, impacting the cooling curves of young neutron stars. Observations of thermal emission from neutron stars combined with careful modelling provide indirect evidence that can support or constrain the presence of these unusual phases. Gravitational wave astronomy provides an additional avenue for testing the existence of exotic matter. During binary neutron star mergers, the tidal deformability of each star depends sensitively on the equation of state and the presence of soft or stiff components in the core. Quark matter or meson condensates can increase the star's compressibility, leading to measurable differences in the gravitational wave signal. Events like GW 17047 have already provided constraints on the stiffness of dense matter, and future detections may allow us to identify the signatures of quark cores or hybrid interiors. By comparing observed waveforms with simulations, researchers can infer whether such exotic phases are likely to exist and how they influence the star's macroscopic behavior. Rotation interacts with exotic matter in subtle but important ways. The reduced viscosity in superfluid quark matter or meson condensates affects angular momentum transport within the star, altering spin-down rates and the evolution of rotational glitches. Similarly, the maximum rotation rate that a star can sustain without shedding mass depends on the stiffness and composition of the core. A quark-rich or meson-condensed core may allow slightly higher rotation rates due to modified pressure support, while also influencing the magnetic field structure through coupling between superfluid components and magnetic flux tubes. Observing pulsar spin behavior provides a window into these deep interior processes. Cooling patterns offer further insight into the presence of exotic matter. Neutrino emission, the dominant cooling mechanism in young neutron stars, is sensitive to the composition of the core. Color-flavor-locked quark matter can suppress certain neutrino channels, while meson condensates can enhance others, producing characteristic deviations from the cooling curves expected for conventional nuclear matter. By comparing observed thermal emission from neutron stars of known age with theoretical predictions, astrophysicists can identify anomalies that may point to the presence of these unusual states. The equation of state, central to modeling neutron stars, is profoundly affected by the inclusion of exotic matter. A core containing deconfined quarks or meson condensates will exhibit different mass-radius relationships, maximum mass limits, and tidal deformabilities than a purely nucleonic star. These variations can be constrained through combined observations of gravitational waves, pulsar timing, X-ray emission, and thermal evolution. Each observational channel provides a piece of the puzzle, and together they form a picture of how matter behaves under conditions that cannot be replicated in terrestrial laboratories. Exotic matter also impacts the star's magnetic and rotational evolution. Superconducting quark cores can alter the distribution of magnetic flux and the coupling between the core and crust, affecting the geometry and evolution of the magnetosphere. This, in turn, influences emission patterns, pulse timing, and the formation of relativistic jets in binary systems or post-merger remnants. Observations of high-energy radiation, combined with precise rotational measurements, allow astrophysicists to connect these macroscopic properties to the microphysics of the core. Ultimately, studying quark cores, color-flavor-locked phases, meson condensates, and hybrid stars allows scientists to push the boundaries of knowledge about the behavior of matter under the most extreme conditions in the universe. Instruments such as NICER, gravitational wave observatories, and multi-wavelength telescopes provide the data necessary to test these theoretical models. Each observation, from subtle deviations in radius to the timing of a pulsar glitch or the waveform of a gravitational signal, carries information about the deep interior. Exotic matter may remain hidden beneath kilometers of dense crust, but through careful study and interpretation, its presence and properties can be inferred, offering a glimpse into a world where quantum mechanics, nuclear physics, and relativity converge in spectacular and unexpected ways. The thermal evolution of a neutron star is a story of heat, energy transport, and the slow balancing act between the core and the surface. Immediately after formation, the star is incredibly hot, with core temperatures reaching tens of billions of degrees. Cooling begins almost immediately, driven predominantly by neutrino emission from the dense interior. Among the most efficient processes is the direct Oerker process, in which a neutron decays into a proton, electron, and electron antineutrino, or the inverse reaction occurs, emitting a neutrino. This process can remove energy from the core extremely rapidly, cooling the star on timescales of thousands of years. Not all neutron stars permit the direct Oerker process, however. In stars where the proton fraction is lower, the modified Oerker process dominates. Here, a bystander nucleon participates in the reaction, allowing momentum conservation while slowing the overall neutrino emission rate. This process is less efficient than direct Oerker, leading to a slower cooling rate and resulting in surface temperatures that remain detectable over millions of years. By observing the thermal emission from young neutron stars in X-ray wavelengths, astrophysicists can distinguish between rapid and slow cooling scenarios, gaining insight into the composition and proton fraction of the core. Superfluidity within the neutron star interior further complicates heat transport. Neutrons in the core can form Cooper pairs, creating a superfluid, while protons may become superconducting. These phases influence both neutrino emission and thermal conductivity. For example, pairing gaps in the superfluid suppress certain neutrino-producing reactions, slowing cooling in localized regions, while the superfluid allows nearly frictionless energy transport, smoothing temperature gradients across the core. Researchers such as Danny Page and Madhapa Prakash have developed detailed cooling models that incorporate these effects, predicting the surface temperature evolution for neutron stars of various masses, compositions, and equations of state. photon emission from the surface, primarily in X-ray wavelengths, becomes the dominant cooling mechanism once the star is several 100,000 years old, and neutrino emission diminishes. The balance between neutrino cooling from the core and photon cooling from the surface determines the observed temperature and luminosity. Instruments like NASA's Chandra X-ray Observatory and ESA's XMM Newton telescope have measured surface temperatures of neutron stars, revealing temperatures ranging from a few 100,000 to over 1,000,000 degrees Kelvin. These measurements, when compared to theoretical cooling curves, provide empirical constraints on internal physics, including superfluidity, composition, and magnetic field effects. The equation of state plays a critical role in thermal evolution. A stiffer EOS produces a larger star with lower central densities, potentially suppressing direct Earth reactions and resulting in slower cooling, while a softer EOS leads to higher central densities, enabling rapid neutrino emission. By combining observational data with theoretical models, astrophysicists can constrain the EOS and gain insight into the behavior of matter under extreme pressure. Variations in mass, radius, and composition among neutron stars mean that cooling trajectories can differ significantly, allowing detailed studies to reveal correlations between observed surface temperatures and inferred interior properties. Accretion in binary systems can alter the thermal evolution. Material falling onto the neutron star surface releases gravitational potential energy, heating the outer layers and modifying the local temperature gradient. This accretion-induced heating interacts with neutrino cooling and superfluid transport, leading to complex thermal profiles that vary over time. Observing accreting neutron stars during quiescence provides additional tests of cooling models, complementing data from isolated stars. Magnetic fields also affect cooling by channeling heat along field lines and modifying the thermal conductivity of the crust and envelope. Strongly magnetized stars, such as magnetars, exhibit anisotropic surface temperatures, with hotspots at the magnetic poles and cooler equatorial regions. These temperature distributions influence both the observed X-ray flux and the interpretation of cooling curves, necessitating models that incorporate both magnetic and thermal evolution. Observational verification of theoretical cooling models has been remarkably successful. Studies of young neutron stars, such as the Cassiopeia A neutron star, reveal cooling over decades consistent with the onset of neutron superfluidity in the core. This provides a rare glimpse into quantum behavior at nuclear densities, where macroscopic thermal properties reflect microscopic particle interactions. Observations of older stars allow researchers to test long-term predictions of EOS-dependent cooling, comparing expected temperatures with measured values to refine models. Neutrino emission mechanisms, both direct and modified Urca, are supplemented by other processes, such as pair breaking and formation in superfluid regions, which can dominate under certain conditions. These processes produce bursts of neutrinos that carry away energy efficiently, influencing the thermal balance and the timescale over which the star cools. The combination of these mechanisms, along with photon cooling, superfluidity, magnetic field effects, and composition variations, creates a rich tapestry of thermal evolution that can be observed and modeled to test fundamental physics. Ultimately, the cooling of a neutron star provides a direct window into its interior. By studying the evolution of surface temperatures and comparing them with detailed models, astrophysicists can infer the presence of superfluid cores, the effectiveness of neutrino emission processes, and the influence of magnetic and compositional variations. Work by Danny Page, Madhapa Prakash, and other researchers has established frameworks for connecting these observable phenomena to the equation of state, rotation, and exotic phases of matter. Every photon escaping the surface, every subtle change in temperature, carries information about the deep, dense interior, allowing us to probe the most extreme conditions in the universe and understand how these remarkable stars evolve over millions of years. The crust of a neutron star, though only about 1 kilometer thick, is a remarkable and dynamic layer, holding the key to some of the most fascinating phenomena observed in these dense objects. As a neutron star spins down over millions of years, losing angular momentum through electromagnetic radiation and particle winds, stress accumulates in the rigid crust. Magnetic torques, especially in stars with strong fields like magnetars, add another layer of complexity, twisting and straining the lattice of neutron-rich nuclei. Over time, these forces can exceed the crust's yield strength, leading to sudden adjustments in the structure, events known as starquakes. Starquakes release energy that can be detected as bursts of X-rays or gamma rays, and in some cases they produce subtle changes in the rotational period of the star. These rotational anomalies are called glitches, sudden spin-ups that occur when angular momentum is transferred from the superfluid interior to the rigid crust. The mechanism involves vortex pinning in the superfluid neutrons of the inner crust. These vortices, which carry quantized angular momentum, can become temporarily trapped by the crustal lattice. When the stress becomes too great, vortices unpin and redistribute angular momentum, spinning up the crust and producing the observed glitch. Theoretical frameworks for this process, including R-mode damping theories developed by Niels Anderson and others, describe how these oscillatory modes can couple the interior superfluid to the crust and affect spin evolution. Observations of glitches across a population of pulsars reveal patterns that inform models of crustal structure and dynamics. For example, the Vela pulsar exhibits relatively frequent large glitches, suggesting a substantial superfluid component in the inner crust, capable of storing and transferring angular momentum. By contrast, older pulsars often experience smaller and less frequent glitches, reflecting changes in superfluid vortex density, crustal rigidity, and the long-term evolution of magnetic fields. These correlations allow astrophysicists to test predictions of nuclear physics under extreme conditions, linking macroscopic observations to microscopic interactions within the crust and core. The impact of crustal dynamics extends beyond individual glitches. The redistribution of stress and angular momentum affects the long-term rotational evolution of the star, influencing its spin-down rate and the alignment of its magnetic and rotational axes. Magnetic field lines anchored in the crust can become twisted during starquakes, altering the magnetosphere and producing changes in emission properties such as pulse shape, intensity, and polarization. In magnetears, crustal fractures may trigger giant flares, releasing energy comparable to the Sun's output over thousands of years in a matter of seconds. Observations of these events, from instruments like Chandra, XMM Newton, and Fermi, provide direct insight into the interplay between crustal physics and magnetic dynamics. The R-mode instabilities of the neutron star's fluid interior are intimately connected to these crustal phenomena. These oscillatory modes, which arise in the rapidly rotating superfluid core, are damped by viscosity and interactions with the rigid crust. The effectiveness of R-mode damping depends on the superfluid properties, crustal composition, and coupling between the core and crust. By studying how rotational frequencies evolve and how glitches manifest, scientists can constrain models of R-mode damping, providing insight into the viscosity, superfluidity, and internal structure of the star. Glitches also reveal information about the distribution of mass and angular momentum within the star. Larger glitches suggest more substantial reservoirs of angular momentum stored in the superfluid, while smaller events indicate localized adjustments or weaker coupling to the crust. Observational campaigns tracking pulsar timing over decades have created detailed catalogues of glitch events, demonstrating that even subtle differences in crustal composition or magnetic stress can produce measurable variations in rotational behavior. These data provide essential constraints for theoretical models, linking nuclear physics to astrophysical phenomena in a tangible way. The interplay between the crust and the core is further influenced by thermal evolution. Cooling affects the rigidity and elasticity of the crust, altering how stress accumulates and is released. Superfluid pairing gaps, which influence heat transport and neutrino emission in the core, also affect the storage and transfer of angular momentum. By combining thermal evolution models with observations of glitches and spin-down rates, astrophysicists can create a coherent picture of the star's internal dynamics, where temperature, superfluidity, magnetism, and rotation are all interconnected. Starquakes and glitches serve as windows into the otherwise inaccessible interiors of neutron stars. They reveal how matter behaves at nuclear densities, how superfluid vortices interact with a rigid crust, and how magnetic stresses propagate through the star. By studying the timing, magnitude, and frequency of glitches, scientists gain information about crustal thickness, lattice composition, and the coupling between crust and core. This information complements other observational channels such as X-ray emission, thermal cooling, and gravitational wave studies, providing a holistic view of neutron star physics. Ultimately, the dynamics of the crust connect microscopic and macroscopic phenomena in a neutron star. Every starquake, every unpinned vortex, and every rotational adjustment is a manifestation of the fundamental physics governing matter at extreme densities. By linking observations of glitches, magnetospheric changes, and rotational evolution to detailed theoretical models, astrophysicists can probe the internal structure, superfluid behavior, and magnetic configuration of these dense stars. The study of crustal dynamics transforms neutron stars into natural laboratories for testing the laws of physics under conditions that are simultaneously extreme, observable, and exquisitely informative. Neutron stars are extraordinary cosmic laboratories, offering an unparalleled opportunity to test the fundamental laws of physics under conditions that are impossible to replicate on Earth. Their extreme densities, reaching several times that of atomic nuclei, create natural environments where general relativity, quantum chromodynamics, superfluidity, and superconductivity converge. The intense gravitational fields, which bend space-time and affect the flow of matter and radiation, allow precise tests of Einstein's theory in the strong field regime. Meanwhile, the dense interior provides a stage for nuclear physics and quantum many-body phenomena, including superfluid neutrons and superconducting protons, revealing the behavior of matter at extremes far beyond the reach of laboratory experiments. Observationally, neutron stars allow us to probe these extreme physics in multiple ways. Pulsar timing, X-ray and gamma-ray emission, gravitational waves, and thermal radiation all provide complementary windows into the star's structure and dynamics. The coupling of rotation, magnetism, and matter under such extreme conditions produces phenomena that can be precisely measured and modeled, offering insight into the interplay between fundamental forces. Instabilities and pulsations, studied by theorists such as Christian Ott and Niels Anderson, provide additional probes, revealing the star's response to perturbations and the physics of oscillation modes within superfluid and superconducting interiors. These oscillations, sometimes observable as quasi-periodic oscillations in X-ray-like curves, carry information about the equation of state, internal viscosity, and the interaction between crust and core. The study of neutron stars also intersects with frontier theories in physics. Holographic duality, originating from string theory and applied to strongly coupled systems, provides an alternative framework to explore dense nuclear matter, connecting gravitational analogues in higher dimensional spaces to the behavior of quark-gluon plasmas and the dense cores of neutron stars. Similarly, hypotheses regarding dark matter capture suggest that neutron stars could act as traps for weakly interacting massive particles, subtly affecting their thermal evolution, rotational dynamics, or even triggering collapse under certain scenarios. These applications illustrate how neutron stars are not just astrophysical objects, but testing grounds for ideas at the cutting edge of theoretical physics. Upcoming instruments promise to extend our understanding even further. The Square Kilometre Array, or SKA, will revolutionize radio astronomy, detecting thousands of new pulsars and providing exquisitely precise timing measurements. Athena, the Advanced Telescope for High-Energy Astrophysics, and LINX, a next-generation X-ray observatory, will allow detailed mapping of thermal emission, hotspots, and surface composition, enabling tests of neutron star crustal and core physics. Next-generation gravitational wave detectors, including the Einstein Telescope and Cosmic Explorer, will provide far more sensitive measurements of neutron star mergers, post-merger oscillations, and continuous gravitational waves from rapidly rotating stars. Together, these instruments will provide a multi-messenger view of neutron stars, connecting the microphysics of dense matter to the macroscopic astrophysical environment. Neutron stars also illuminate extreme magnetic and rotational physics. Magnetars, with fields exceeding 1,000 trillion times that of Earth, and millisecond pulsars, spinning hundreds of times per second, test the limits of magnetohydrodynamics, angular momentum conservation, and superfluid dynamics. Observations of starquakes, glitches, and giant flares reveal the interactions between crust, core, and magnetic field, while thermal and X-ray emission provides constraints on interior composition and equation of state. In this way, neutron stars function as natural laboratories for a remarkable range of physics, from quantum many-body theory to strong field gravity. Beyond individual stars, neutron star mergers offer additional opportunities to probe fundamental physics. Gravitational waves and electromagnetic counterparts from events like GW 17047 reveal the properties of dense matter, nucleosynthesis of heavy elements, and the behavior of matter under tidal stresses. The post-merger remnants, whether hypermassive neutron stars or black holes, provide further insights into angular momentum transport, magnetic field amplification, and neutrino emission in extreme environments. By comparing observations to simulations developed by groups led by Masaru Shibata, Luciano Rezzolla, and others, scientists can test the consistency of theoretical models and refine our understanding of matter at nuclear densities. Neutron stars also pose profound open questions. The exact composition of the inner core, the presence and nature of exotic matter such as hyperons, deconfined quarks, or meson condensates, the mechanisms behind magnetar flares, and the limits of spin and mass all remain active areas of research. Multi-messenger observations, advanced simulations, and laboratory experiments in nuclear physics and quantum chromodynamics work together to address these questions. Each new detection, whether a pulsar, a magnetar flare, or a gravitational wave signal, adds another piece to the puzzle, informing both astrophysics and fundamental physics. The rotational dynamics of neutron stars, including R-mode instabilities, superfluid vortex behavior, and glitch phenomena, continue to challenge models of dense matter and internal viscosity. By analyzing long-term timing data from radio pulses and combining this with X-ray and gravitational wave observations, scientists can infer internal properties that would otherwise be inaccessible. These studies connect the macroscopic behavior of stars to the microscopic interactions of neutrons, protons, and possibly quarks, creating a bridge between nuclear physics, quantum mechanics, and astrophysics. Thermal evolution and cooling provide additional experimental constraints. Observations of surface temperatures, combined with models incorporating superfluidity, superconductivity, neutrino emission, and exotic matter, allow the testing of hypotheses regarding the internal composition and equation of state. Instruments such as NICER continue to provide precise data on mass, radius, and surface temperature, allowing detailed comparison with theoretical predictions and constraining the range of possible interior structures. Ultimately, neutron stars serve as a nexus where multiple domains of physics converge. They test general relativity under extreme curvature, reveal the behavior of matter at nuclear and supranuclear densities, explore the dynamics of superfluids and superconductors, and illuminate the interaction between magnetic fields, rotation, and radiation. They allow astrophysicists to examine processes that operate at energies, densities, and field strengths far beyond terrestrial experiments, offering insights into the most fundamental questions about matter, energy, and the universe. As we look to the future, the combination of advanced observatories, multi-messenger astronomy, and theoretical innovations promises to deepen our understanding of these extraordinary stars. From gravitational waves to high-energy radiation, from superfluid interiors to exotic quark cores, neutron stars will continue to provide a window into physics at its most extreme. They are living laboratories, continuously challenging our understanding, revealing new phenomena, and guiding us toward answers to some of the most profound questions in astrophysics and fundamental physics. Each pulse, flare, and gravitational ripple is a message from nature itself, inviting us to explore the boundaries of knowledge, to test our theories, and to marvel at the extraordinary behavior of matter in one of its most extreme forms. Our journey has taken us from the life and death of massive stars to the astonishing extremes found in neutron stars, the remnants left behind when gravity overpowers nuclear fusion, and compact stellar cores to densities far beyond what we experience on Earth. We have traced the evolution from hydrogen and helium fusion chains through silicon burning and core collapse supernovae, understanding how the interplay of mass, rotation, metallicity, and magnetic fields sets the stage for the formation of these extraordinary objects. In their birth throes, neutron stars become laboratories for physics under conditions that challenge the imagination, where gravity, quantum mechanics, and nuclear forces intersect in ways impossible to replicate in any terrestrial experiment. We have explored how neutron degeneracy pressure, as envisioned by Lev Landau, supports these stars against further collapse, while superfluidity and superconductivity within the core influence rotational dynamics, glitches, and thermal evolution. The layered interior from crust to outer and inner core presents an intricate environment where nuclear pasta, hyperons, and possibly deconfined quark matter shape the structure, cooling, and emission properties of the star. exotic phases such as color-flavor-locked quark matter, Bose-Einstein condensates of kaons or pions, and hybrid stars expand our theoretical understanding, connecting microscopic particle interactions to macroscopic observables like radius, mass, and magnetic field evolution. Rotation, angular momentum conservation, and R-mode instabilities govern pulsar behavior, while accretion in binary systems can spin stars up to millisecond periods, producing recycled pulsars and driving relativistic jets. Magnetic fields, often amplified to strengths trillions of times greater than Earth's, influence both crust and magnetosphere, producing flares, X-ray bursts, and gamma-ray emission. Observations of pulsar timing, surface temperature, and multi-wavelength emission provide insights into the internal physics of these stars, allowing us to probe the equation of state, superfluidity, and magnetic dynamics in ways that link theory directly to observation. Binary mergers have revealed yet another dimension, where neutron stars collide in spectacular events that produce gravitational waves, kilonovae, and our process nucleosynthesis, enriching the universe with heavy elements. The work of Masaru Shibata, Luciano Rezzolla, and others in simulating these mergers has shown how hypermassive remnants, magnetic amplification, and tidal interactions are sensitive to the internal composition and stiffness of matter, allowing multi-messenger astronomy to constrain the equation of state in unprecedented ways. Gravitational wave events like GW 17047 have transformed our understanding, connecting extreme astrophysical phenomena to fundamental nuclear physics. Throughout this exploration, we have seen that neutron stars are defined by a combination of extremes: density, spin, magnetism, and radiation, all intertwined with exotic states of matter. The cooling and thermal evolution reveal the microphysics of neutrino emission, superfluid gaps, and crustal conduction. Starquakes and glitches provide glimpses into angular momentum transfer and crust-core interactions. High-energy flares, X-ray bursts, and pulsar wind nebulae demonstrate the dynamic behavior of the magnetosphere and the consequences of particle acceleration under intense fields. Exotic cores, quark matter, and meson condensates illustrate the ways in which fundamental forces interact under conditions unreachable in any laboratory. Observations, theory, and even careful speculation have combined to create a holistic understanding of these remarkable objects. Instruments from N, ICER and Chandra to LIGO and Virgo, and future observatories like SKA, Athena and Lynx promise ever more precise data, allowing us to test predictions about mass, radius, rotation, magnetic fields, and interior composition. Theoretical frameworks from relativistic stellar perturbations explored by Eric Poisson to instabilities studied by Niels Anderson and Christian Ott provide models for interpreting these observations and linking them to the underlying physics. As we reflect on neutron stars, we are reminded of the subtle elegance and profound complexity of the universe. These stars, no larger than a city yet packing more mass than our sun, spin, pulse, flare, and cool in ways that reveal the interplay of the strongest forces known. They challenge our understanding, inspire our curiosity, and act as cosmic laboratories where the extreme becomes accessible to human observation and reasoning. Each pulse we detect, each flare we measure, is a message from the universe about the nature of matter, energy, and space-time. In the quiet awe of contemplating these stellar remnants, we find a sense of calm and wonder. The universe has provided us with objects that stretch the imagination, yet through observation, simulation, and theory, we can begin to understand them. Neutron stars are not only the remnants of stellar death, but also gateways to knowledge, linking the microscopic world of nuclear and particle physics to the macroscopic universe. Their study teaches us patience, precision, and the value of curiosity, reminding us that even the most extreme phenomena can be observed, understood, and appreciated. As we close this journey, we leave with a gentle sense of awe, a recognition of the delicate balance of forces and processes that create these cosmic marvels, and an enduring curiosity about what more they can teach us. Neutron stars invite us to continue exploring, to question, to measure, and to marvel at the extremes of physics, space, and time, offering a calm yet profound reflection on the extraordinary universe in which we live.